Alright, so in this problem, we're going to assume that the circuit is hooked up to a 50-volt power supply. So between here and here, there's a power supply hooked up. And we want to find the equivalent capacitance, the charge on each capacitor, and the potential across each capacitor. Alright, so the first thing I'm going to do is find the equivalent capacitance. So as I go along here, these two are in series, but they're in series with this set of parallel capacitors. So I'm going to first reduce this down to equivalent capacitance. Then I'll have three capacitors in series, and then I can find the final equivalent capacitance. So since these two are in parallel, I'm going to add the 7 and the 9 together to get 16. So that gives me this relationship here. And then I have a 2, a 4, and a 16 then in series each other. So I'll do 1 over 16 plus 1 over 2 plus 1 over 4, and then take the inverse to get 1.23 microfarads. Alright, so my goal now is to find the potential and the charge on the capacitors. And there's a reason why I always draw these diagrams like this, because it helps us backtrack through and identify where we're in series and where we're in parallel. So because when I step back between my equivalent capacitor and the previous step, they're all in series with each other, that tells me my equivalent capacitance allows me to calculate the charge flowing through the circuit. So I'm going to take capacitance equals charge over volts, and I've actually started this up here. I'm going to take my equivalent capacitance for the circuit and the power supply, so the voltage from the power supply, and that gives me the charge. So that's the charge that is flowing from here through here, and then splits here, and then comes back in here. So that's the charge on 1 and 2. Now remember, when they're in series, the charge is the same. When they're in series, the potential is different. So I'm now using the individual capacitances and the charge that is flowing through each of those capacitors to find the potential. So for the 2 microfarad, we're going to get 30.75 volts. And for the 4 microfarad capacitor, we're going to get 15.38 volts. So I've taken care of 1 and 2, now I need to deal with 3 and 4. Now I know that between here and here, in each of the branches, there's going to split 61.5 microfarads. So I'm going to use the equivalent capacitance and the charge that splits in between the two to find the potential. So we're going to take the 16 equals 61.5 divided by the voltage. The voltage is going to be 3.84. And because they are in parallel, that voltage is going to apply to both 3 and 4. I can then use the individual capacitance of the capacitor to find the charge. So how much goes to the left, how much goes to the right. So 7 microfarads times 3.84 is 26.9 microcoulombs, and 9 microfarads times 3.8 volts gives you 34.6 microcoulombs. So notice I'm leaving things in microfarads and microcoulombs. That saves you from having to write 10 to the minus 6 through a whole way through this work, so it just saves you some space. And this works as long as the capacitance and the charge are both in the same metric prefix. So as long as they're both micro or both nano, you'll be okay. One other thing I want to note before I exit this video is that if we had stepped back here to here and found that they are all in parallel with each other, then the voltage for that parallel setup would have been the voltage from the power supply, and then you would have needed to calculate the individual charges. So it's different if you step back from here to here and find series compared to when you step back here to here and find charges in parallel. And I do have an example where you step back and they are in parallel in my extra example problems.